So this is the demo for Webb Protocol. It is both a Tornado Cache mixer and the bridge put together. So it allows you to deposit and withdraw within the same chain if you'd like to, but if you'd like to also bridge, it makes it possible. So it is currently only on testnet, and to be honest, I actually had some issues with the application here. But the basic idea is that you need to copy this and you make a deposit. And once the transaction goes through on Hopston, you would be able to just put the transaction node here and the address that you want to withdraw. You obviously would like to go to the wallet that you're trying to withdraw from, not use the same wallet, because if you do this, everyone will know who sent the transaction. You could try to use the relayer, which is the actual safest option, but I also had issues with the relayer earlier, so as I said, it is currently only on testnet, and yeah. So this is the idea. You bridge, you get the Webb WETH, and you can then unwrap onto actual ETH. And yeah, that's pretty much it. I don't think we need to actually go through the thing because everyone understands what's going on here. So before actually getting into the code, I'd like to present how I think of Webb, basically. So if we were to open this, get it into full screen and zoom a bit. Okay. So this is how Webb works if we completely ignore the fact that it is a mixer. So basically, you send a transaction on a source blockchain that deposits onto the anchor of that chain. Whenever that transaction succeeds, the relayer sends that transaction onto a bridge contract on the destination chain. So this is another blockchain. This bridge contract will then parse the input sent by the relayer, which will then be able to reconstruct what is the function that it should run on the smart contract side. And aside from this, if we were to look at the apps, we basically got three apps there, and they are the mixer, the anchor, and the V anchor. The mixer works just like Tornado Cache does, so you store the hash of the nullifier and the secret. This is your commitment. On the anchor, it's the exact same thing, but you append the chain ID to that. And on the V anchor side, you append also amount, and the secret becomes a blinding term because the actual secret we're trying to call here is the amount. So blinding, if we were to just ignore the blinding and hash this, it would be very easy to find what the destination chain was and parse all possible amounts of ETH. I mean, you cannot have that much ETH after all. So that would leak your public key. In order to not leak your public key, we use this blinding term that adds a lot of entropy to the hash. So that's the basic idea. So let's jump into the code here. Looking into the contracts, there's the signature bridge. It is the bridge contract. It chooses which executor is going to execute the proposal, and it's pretty much just going to parse the data that was sent by the relayer. So if we go into the execute proposal here of the anchor handler specifically, we can see that it either is setting a handler or setting a verifier, or it's updating an edge on the Merkle on one of the Merkle trees, and or it's configuring stuff. So this is most likely the most common function that's gonna be called, and it is pretty much a deposit. Okay, this is the code that's going to get the interface with the user. So only the anchor proxy has been implemented. So we can only deposit on testnet fixed amounts right now, but the v anchor is already working. It's just not the proxy is not here, so there's some stuff that we need to actually keep doing, but we're getting there. Uh, so you can deposit and withdraw, and this is just a proxy to the actual contract, which is here. This is the fixed deposit anchor, and this is the actual pool the tornado pool. This is the tornado pool that also accepts the bridging. So you can deposit and you can withdraw, and there's some. The code's big. I'm not gonna go through it all, so I'm just gonna get you the main idea. You can read through the code, and it's going to explain most things. The v-anchor stuff is mainly here. So as I already shown on the drawing I made, uh, it is the same stuff. It just uses the UTXO format. It's the same thing that Tornado Cache is not trying. They're doing it on Tornado Nova. We just ported that onto the the Webb protocol. So it's the same thing. And going on to the circuits. So going into the circuits now, the anchor and the withdrawal. Let me zoom in a little bit. Yeah, I think this is better. Yeah, okay. So this, if you're familiar with Tornado Cache, should be very familiar to you because we're using exactly the same structure. So instead of just using the hash of the nullifier and the secret, we're using the hash of the chain ID together with those two. And now instead of only checking if our transaction is in one Merkle root, we need to check if it's in one of a set of Merkle roots, because we now have many Merkle roots since we have many chains attached. So that's the idea of the anchor circuit. On the v-anchor side, we can look at the transaction, and it works a little bit differently now, but if you're familiar with Zcash, this should be very familiar to you as well, because it's the same logic that they use. So let's roll back a little bit just to understand where we're at when we're trying to run this function, and then we're gonna explain how we're gonna do that. So basically, we already have an amount deposited onto the blockchain. So let's say I got 1 ETH. I could create a new transaction now that's gonna send this amount to a new public key, for example. So this is what this transaction function does. It creates from the public amount that you previously had two new transactions, one that's going to stay, it's basically the change that you got, and one that's going to spend the money. So for every transaction you get two inputs and two outputs, and yeah, okay. So we got many things here, but basically we're looking for each one of them. We're computing the commitment and the hasher and the nullifier actually. So we're computing the commitment hasher and the signature to then compute the nullifier hasher here. And this for every one of the transactions there was inputted. So the 2 ones or the 16 ones, we're currently talking on 2, but it also supports 16.2 style, but whatever. So we basically now check if the transaction is inside one of the valid Merkle roots. And we need also to check that the sum of the inputs plus the public amount is equal to the sum of the outputs, because you're going to spend the money, so you cannot create money out of the out of thin air. And so yeah, this computes the commitment hasher for the output. Yeah, I think this is the relevant parts. So yeah, that's it, I think.